So good morning, everybody, and welcome to this new seminar at the Instituto de Astrofísica de Andalucía. Today, we will have the talk by Dr. Laura Hermoso Muñoz, that she's working at the Centro de Astrobiología in Madrid, Spain. And she will talk about outflows in AGNs from low to high luminosities, the case of NGC7172. Dr. Laura Hermosa, she's 1 year old doctorship, so congratulations. Did her degree at the University of Oviedo here in Spain and her master at the University of La Laguna in Tenerife, where she centered her investigation in dwarf galaxies in the local group. She did her PhD here at the Instituto de Astrofísica de Andalucía, working in the AGN groups and in searching for outflows in low luminosity AGNs. Now she's working as a postdoc at the Centro de Astrobiología in Madrid, analyzing AGNs with the James Webb Space Telescope data. She's part of the European Consortium of MIRI, Guaranteed Time Observations, and the GATOS collaboration. So thank you very much, Laura, for being here, and the floor is yours.
Okay, so thank you, Ronald. Thank you, everyone, for being here. So for those of you that already are familiar with my work, the first part of the talk is going to be, again, the same thing. But I'm going to center this presentation in two main parts. So the first part is the work that I've been doing here at the IAA during my thesis, and then I'm going to jump onto the work that I'm doing with the JWST data, which I guess that is the part in which you all are more interested in. So let me start just a very small introduction about AGNs, because I guess that you are familiar with them already. So basically, active galactic nuclei are very special regions in the center of galaxies that are very compact and impact heavily the evolution of the galaxy. So they are known because they emit a large amount of energy in many different spectral bands. And there are many different types that are more or less summarized in that picture, depending on the level of accretion that the black hole, the supermassive black hole, is having, and also the point of view with respect to with which we see the object. One of the most important things related to AGNs nowadays are outflows and feedback, not only AGNs but galaxies in general, basically because outflows are known to impact, or are thought to impact the evolution of galaxies in many aspects. And so there are many things that one can do studying this kind of outflows that are essentially gas that is emerging from the central parts of the galaxy. So we can study them through the kinematics of the gas, the energetics, how they impact the stellar formation, the relation that the outflows have with the host, and so on. And one of the first questions that people wanted to address related to outflows in galaxies is if they are common in galaxies, and in particular in AGNs. And so very recent work that it has been done with respect to this basically has tried to study outflows, taking into account their multi-wavelength nature, meaning that for having a complete view of outflows in AGNs and in galaxies in general, one has to take into account all the different phases of the gas, molecular, ionized, neutral gas, or X-rays, or other components. And we end up with this kind of relations in which one can see that we are relating the properties of the outflow, in this case the mass outflow rate, with respect to the properties of the AGN, in this case is volumetric luminosity. And some relations started to appear, like this one, in which depending on the gas tracer that you are using, we found different relations, but all of them agreed at some point that the larger the volumetric luminosity, the stronger the outflow. So there seems to be a relation in there, so that in the low luminosity end of the AGN family, the outflows are expected to be fainter. But this relation has been changing lately. So if we focus, for example, in other work, we see that the initial trend that was mentioned in Fiore's plot, now it seems that the new data is slightly offset from the initial relation. And it's not just one work, there are several works that are seeing much more dispersion in this kind of plots. But in all of these works, the thing is that we don't know what happens at low luminosity, because none of them are tracing volumetric luminosities smaller than 10 to the 43 Earths. So that's where we were focused on in this part. So how does this relation change if we include this low luminosity end? And the reason why it's not populated is that, as I told you, in this region, the outflows are expected to be smaller, so then, less powerful, sorry. So then their study should be a bit more complicated, and people were focused just on obtaining the global properties of outflows in more luminous AGNs. So if we focus on liners, which are the majority of the population of AGNs in the low luminosity end of the family, we don't know if outflows indeed exist in these systems. So here you have an example of a liner which is NGC4438, in which already with these really nice images from the JWST, we are seeing a bubble emerging from the center. So apart from this, there are some other individual discoveries of outflows in liners, but there is no systematic search until the work that we did here. And one of the main motivations of studying liners is because these are the most numerous AGN population in the local universe, and this allows us to do spatially resolved studies of these objects, despite the outflows are expected to be smaller. So we started, one of the things that we did was to do a systematic search for the first time of outflows in liners, and for that we gathered a sample of 70 nearby liners, which is the largest atlas up to date of looking for ionized gas morphologies in these objects. And so we did a systematic search using optical imaging with proprietary data from the NOT telescope and also HST data from the archive, all very nearby objects. And what we did was essentially to see how the ionized gas was distributed on these galaxies. So we end up finding 4 different categories for the ionized gas, so that are shown here. The first one would be core halo. Essentially, the gas is concentrated around the center of the galaxy. Then we have disk halo, that is the gas that is oriented along the galactic disk or along the spiral arms or nuclear rings. Then we have the bubble-like, which are the ones we are interested in, basically referring to gas that is in a bubble-like shape or biconical shape, or essentially filamentary, not related to any other specific structure of the galaxy. And then we have dusty, which is whenever we have that dust lane covering the nuclear part. So using the middle, the percentages in which we detected each category, and the one that we detected the most galaxies is the bubble-like. Although, of course, imaging alone is not sufficient to actually claim that we are detecting outflow. We're just detecting gas that is behaving otherwise, not as the galaxy itself. So that's why we complemented this with kinematical information from the literature. And for all the 70 objects we detected, we found kinematical information from 60 of them. Half of them were coming from interval field spectroscopic data, which is nice because interval field spectroscopic data allows us to actually characterize better the behavior of the gas in these systems. And from those 60, we found that half of them had a reported detection of an outflow or an inflow, which this is setting for the first time a percentage of detection of outflows in liners that was missing until now. So we have now a great amount of candidates for hosting an outflow, and now we have to characterize them. So that's the second part of the talk. That is the analysis that we have done in a small subsample of these liners to actually try to see if we were indeed detecting an outflow and we characterize them. So for that, we use MEGARA. MEGARA is an integral field unit that is located at the GTC telescope. And the great advantage of MEGARA is the high spectral resolution that it has, going from 6,000 to 6,000 to 20,000. And these are the main characteristics of the sample. These are just optical images of the 9 galaxies that we selected. And so we started, first, for giving you an overview of what the analysis was like. First, one of the most important things to characterize the ionized gas is that we have to model the continuum, basically because these liners, as I've mentioned before, are really low luminous objects, which means that they are heavily impacted by the emission of the galaxy. So we really need to get rid of the continuum to actually obtain the true emission from the ionized gas. So here you have an example of the modeling in several bands of MEGARA that go basically covering from H beta and oxygen 3 to H alpha and sulfur 2 and so on. That we use the PPXF code for the modeling. And then we did an emission-line modeling. Here you have an example for one of the galaxies. We model the emission lines using Gaussian components, allowing up to 4 different Gaussian components if needed, one going for the broadline region if present. And basically we order them to ensure continuity in all the maps. So we started this project with NGC7172, which is a prototypical liner. It's a work that is already published. And then we continued with the whole sample. And I have to say here that 3 of the galaxies are coming from the GATOS survey, which is a survey for exploiting the guaranteed time of MEGARA. And this is a work that is already under referee revision. So let me start with NGC7172. So as I mentioned, this is a prototypical liner really close by a galaxy. And it's the AGN is living in an early type galaxy where it's known to have a radio jet. And in the images, I'm plotting the field of view of the data that we have. So in red is the field of view of the MEGARA data. And we also had MIUS data for this galaxy, for which we did a mosaic that was basically covering all the emission from the galaxy. These are the main results of the analysis. So in these maps, we have velocity dispersion, and flux. You can see that basically we are mapping the ionized gas in the whole field of view of the galaxy. These maps correspond to the oxygen 3 line, and what we can see is essentially that the gas is rotating. But if we focus on the inner regions and we look to the velocity dispersion, we are seeing some peculiar structure that wasn't expected at first for a regularly rotating system, and that has this strange butterfly-like shape. The curious thing is that we detected more than one component, as I've told you before. And if we plot the first component with respect to the second one, what we see is that they are more or less perpendicular, and the velocities are quite different, also the velocity dispersion. And in fact, we found that this secondary component has more string kinematics, and it's oriented along the direction of the radio jet. So what we have done here is to interpret all of this picture as an outflow that is expanding as a consequence of the presence of the jet. And due to this expansion, it's creating a cocoon of low density gas, which is this butterfly-like gas. And if we were able to derive the properties of the outflow, and we are seeing that the outflow is indeed really weak in comparison to the ones that we detected in more luminous AGNs. And also it is consistent with being jet-driven, given their energetics that we derive. So, okay, we are now seeing an outflow for the prototypical liner. What is going on? What happens with the rest of the galaxies? Well, we detected outflow for 6 out of the 9 objects, and Each of them has its peculiarities, as I cannot go through all of them, and I have picked 2 examples to show you what the data looks like. And the first one is NGC3226, that is this galaxy over here, that is interaction. And what we see is that the primary component of the gas is basically gas that seems to be rotating along the disk. However, we are detecting a secondary component that is basically concentrated in the PSF, and all the maps have the same are in the same scale. So you see that the kinematics of the secondary component are quite different from the primary component. And if we look a bit closer to the velocity dispersion map, we are also seeing this butterfly-like shape that we were hinting with NGC1052. That is this enhanced sigma region oriented perpendicular to the direction of the disk, and which is co-spatial with the presence of the secondary component. That is clearly broader than the primary component, and also is completely blue shifted. So we interpreted this component as a weak and compact outflow, that in this case there is no radio jet, so it's more likely AGN driven outflow. And this is the situation that we have for many of our targets, so some unresolved emission in the center, but we have other objects, as is the case of NGC4438, in which the emission is more resolved. So I've already shown you this image before, and you see in the right part of the image a close-up view of the inner regions. So it's an H-alpha image of the galaxy, and you see that we can trace the outflow very nicely with the H-alpha emission. So this is what the MEGARA maps looks like. So we detected 3 different kinematical components. The first one, so as the case for NGC3226, seems to be like gas rotating along the direction of the disk, which is marked by that black line. But then the secondary and the third component have really different kinematics from the disk component. So what we have interpreted here is that the secondary component looks exactly like the bubble of gas that was already traced with H-alpha. And we see, for example, that the velocity dispersion is enhanced in the borders of the bubble. So this could be related to shocks as the bubble expands through the medium. And of course, the flux is just the bubble. And then the third component that again has very different kinematics from the other 2, we have interpreted it as related to radio emission that is seen in that direction. Okay, so now in general, how do these outflows compare with other AGNs, and how do they fit in the relation of Fiore that I've shown before? So this is what we have found. So this is the same relation as in interaction. We have the volumetric luminosity versus the mass outflow rate. So the crosses are the Fiore's plot, and this line would be the initial relation by Fiore. And these colored points are our liners. So what we essentially are seeing is that we are completely out of the relation. We are above the values that were expected for this kind of outflows. So this is telling us that these outflows that we're detecting in liners are stronger than were initially thought for these AGNs. But also, in any case, we are finding very compact outflows with parsec scales outflows, and deriving their energetics, we are seeing that these outflows definitely are not able to quench the host galaxy, so they are not expected to have a huge impact on the evolution of the gas content of the system. So now what we are seeing in this new picture is that if we go to low luminosity, and in fact if we take a luminosity range from 10 to the 41 to 10 to the 45 approximately, we have a really high dispersion on the measurements of the mass outflow rate. And we are not the only ones that are working on this. And in fact, this really high dispersion on the mass outflow rate is the motivation of the work that I'm doing now. And now I'm going to jump to the third part of the talk, which is the analysis with the JWST data. So with the GATOS project, that is a project that is focused on analyzing activity in galaxies through many different data sets on many different aspects. So searching for Torus, Outflows, and so on. We have this JWST program that aims to understand why we found this really large dispersion on the first relation. So this project has selected 6 galaxies. All of them are Seyferts that have very similar volumetric luminosity, but have a difference of 3 orders of magnitude on the mass outflow rate. So the aim here is to try to understand what is the physics behind that could be driving that these outflows are actually so different. And so for that, we have selected JWST data. Just to give you an overall impression in case that you are not familiar with JWST data yet. So we have, so all this data is based on MIRI, the MIRI instrument. MIRI is the medium-infrared instrument of the JWST. It has several observing modes, so imaging, coronagraphy, and spectroscopy like 2. In this case, we're focused on the MRS mode, which MRS means medium resolution spectroscopy. Basically, it's an eye view. So again, data cubes as for MUSE and MEGARA. And it has 4 different eye views that are divided in what we call 4 different channels. So each of them has slightly different properties of field of view, spatial, and spectral resolution. This is just an overview impression of the eye views that work very similar to MUSE. And at the end, what you have is 12 different data cubes that are covering a total wavelength range from 5 to 28 microns approximately. So each of the cubes has slightly different efficiencies and slightly different properties. The smaller field of view that we have is approximately a square of 4 times 4 arc seconds, and the largest is 7 times 8 arc seconds, more or less. Okay, so from all the 6 galaxies, I'm focused on one of them, which is NGC7172. This is a type 2 Seyfert, a really beautiful, almost edge-on galaxy. Also, again, very close by, and the luminosity the same as all the others. And for this galaxy has been already studied through many different data. So it has been analyzed with MUSE already, also with Symphony, with ALMA, and it's known to host a nuclear ring, which is almost edge-on again as a galaxy. And one of the most important things of this galaxy, and the thing that we are more interested about, is that there is a detection of an outflow in several phases. So with MUSE, it was detected an ionization cone that was going from north to the south part of the galaxy. And later on, it was corroborated the presence of an outflow, also using Symphony data, mainly with the ionized gas. And in this case, you see that it was more detected towards the south part of the galaxy. And also, it was some tentative detection of a molecular gas outflow, again, in the southern band direction of the galaxy. So this is what the integrated spectra of one of the channels looks like for this galaxy. So you can see that we have, well, I have divided the 3 different bands just to give you an overview of the complexity of the spectra. And you can see that we're finding many different emission lines. So there are many things and many studies that what one can do with this kind of data. One of the things that we can be focused on is the molecular gas, because we have detected many emission lines corresponding to the warm molecular gas. In this case, with that, we can study excitation, we can derive, of course, the properties of outflows, if any, and also properties such as the column density of the gas and so on. Other thing that one can do with this kind of data is focus on the ionized gas, which is basically the thing that I'm doing right now. And through this, we have low ionization gas and high ionization gas, and each of them is telling us something different. With this, of course, we can derive line ratios, talk about metallicities, excitation, and outflows and inflows. And for this galaxy, we are not seeing them, but for some others, we also have these PHS features that can be really strong for some of the JWST galaxies. And with that, we can trace basically how the dust behaves in these systems. To give you again an overview of how complicated the data can be individually, here you have two screenshots that have been done with COFIT view of two different parts on two different cubes of the galaxies. And here you have neon 5 line and oxygen 4 line. We are immediately seeing that there are two peaks, so actually we are seeing a very complex profiles that need to be modeled pretty carefully. So for that, we have started using Alucine, which is a code that was published in this paper by Luis Peralta in 2023. That basically what it does is to model the spectra with Gaussians. So it can do fitting for MUSE, MEGARA, and also JWST data. And it's very powerful tool, and also it's very quick. And we have complemented it with a self-developed code also to do the modeling and compare, and with a non-parametric analysis of the emission lines, because in this case, the two components are quite separated one from the other. So to give you an overview of what we are getting, this is all preliminary work. You have the maps velocity, velocity dispersion, and flux. For two emission lines, the first row corresponds to H2S19, so one molecular gas, and the second row corresponds to neon 6, which is one of the highest ionization emission lines that we are seeing. And you can see that already the picture is quite different depending on what line you are seeing. So this is just a model with one Gaussian for light, okay? So in the top part, we see that the molecular gas is very nicely traced in the disk. That is, we see it in the flux. We see a slightly high enhanced dispersion again along the disk, and this really nice velocity rotation map. So in the velocity dispersion, we found some like blobs corresponding to H2 regions, because as I have mentioned, there is a nuclear ring right there. But if we focus on the high ionization emission lines, we see a completely different picture. In this case, we are not tracing the disk, but we are tracing this H-shaped gas that is more likely the ionization cone that was already seen. So, but in this case, the big difference is that we are also detecting this ionization cone in the northern part that was not detected neither with the optical or with symphony or with force. If we do an analysis of two different components, now we can actually see the outflow. So here you have the maps for the oxygen 4. So now the maps are a bit changed. Here is the flux, velocity, and velocity dispersion, first and secondary component. And what you can see is that the first component could be related to the disk, also could be related to the outflow already. And then the secondary component that is more prominent to the south, that is probably related to the outflow that was already detected with MUSE. On the right part, I'm putting some integrated profiles of the emission lines. So again, we see very broad profiles and two components that are easily seen. So with that, we can do the parametric analysis that basically relies on detecting where is the peak of the emission and where do we find the largest velocities of the line. So in this case, we can derive these parameters that are B10, B50, 90, and 98, but tell us more about how the outflow behaves and what is the speed and so on. And we are finding similar values to what were found in the paper by Davis et al. That was with optical data. for the outflow velocity. So this is telling us that indeed this emission is probably the outflow that we were looking for. And so with that, I just come to my summary that I did it in a different way, just in case I have bored you and there are no questions. That is, I'm doing some questions for you instead of you for me. So what we are seeing is that indeed outflows are common in liners, and we see that the majority of them are compact, and they seem to be stronger than they were initially seen. So are they actually weaker than are the models that we think about outflows in liners, right? Or is just a matter that they were not detected before? Also, we have this really large scattering in the mass outflow rate plot versus volumetric luminosity. We don't know what is the origin yet of this. How can the mid-infrared information help here? Can we find something that we have not seen before? Or is it just that the assumptions that we are having for estimating these parameters maybe are not completely correct? So we have to come back, so we have to take a step back and see what are the differences on velocities, maybe on the estimations of densities and so on. And with that information, maybe you can redo this plot and have some more significant comparison. And that's all that I wanted to say. Thank you.
Thank you very much, Laura, for these wonderful results. So, questions? Oh, is that?
And it's just one of the plots you're showing for James Double Webb, JWST, that one. Then some white points in the molecular gas. Why is it that?
So we have some problems there when the AGN is really strong in the center, because some of the lines are heavily impacted by the continuum. And sometimes, especially with the molecular gas, we cannot fit the lines in a spaxel by spaxel basis. So for the central parts, the trend now is to work with integrated spectra, basically, because if the AGN is really strong, we cannot see the lines as clearly as for other objects. And this is happening in the molecular gas. So, for example, with the neon 6, we don't have that problem. But yeah, thank you.
Questions?
Yes, could you please go back to where you saw us the plots of neon 5 around 4 measurements? That neon 5 measurement is the one at 24 microns or at 14 microns?
24.
24. And you saw us the simplified. And can you compare that one to the neon 5 14 microns?
Yes, and I have the line ratio, but I cannot show you yet. In any case, if you do the line ratios also with other neon 5 species, it's really nice because we are actually seeing the ionization cone really, really nice.
Such a big.
Questions?
Yeah, you pose the questions to us, but I resend them to you. So what would you ask to your own questions at the end?
No, so I guess that I'm not sure if this relation makes sense anymore, because for obtaining these mass outflow rate values, you need to assume density, you need to assume velocity, well, assume or estimate velocity, also the radius of the outflow, and so on. And for all of that, you need to make some assumptions that not everybody does the same assumptions, no? And all of these parameters impact really, really much this distribution. So I guess that one of the things that needs to be done is actually going back to analyzing all the parameters individually. So not plotting volumetric luminosity against mass outflow rate, but maybe against velocity, against radius, see how that parameter changes, and then see how they can propagate into this Because if not, we are just mixing things that maybe doesn't make sense, no? So in this case, for example, where you know that for aligners we are finding densities of order of 100, 1,000 as much. But for example, the triangles from Baron et al. Assume densities of 20,000. So a difference on 2 orders of magnitude then implies also huge difference on the mass of flow rate. So maybe we should come back to analyzing individual characteristics and prior to deriving these properties. That's my guess.
More questions? Laura? Eva?
Laura, coming back to the that you saw the previous line distribution. Where is the narrow line in this galaxy? Well, I mean, one expect that these lines trace very well the narrowing region.
Yeah.
So, are you allowed to separate the narrowing region from the subfield region?
Well, this is an issue. I mean, where does the outflow start and the ionisation cone? Where is the narrowing region? In that sense, I think that we need to analyze all the lines at once. I mean, because probably are going to analyze these lines that are low ionization emission lines can trace better the behavior of the narrowing region. But this is a work in progress. I mean, it's not only the fits that we do with Gaussian, but also I guess that the non-parametric analysis is going to help, because in this case, the outflow component is really quite well defined. So yeah, but of course we have to take it carefully, the analysis.
Yeah, one question about the last slide.
Yeah.
The problem here is that you are assuming at least independent, because you have a determination more or less okay, or the okay, and the flow is using itself. But you need to determine where is the radius, where is your cubic, that is divided by it. Then depending, the relation is supposing a constant radius probably, okay? And it's not true when you go to the inner part of the outflows in the perineal part of the broad line region with reverberation, you can have an idea of the radius, okay? But with other lines, really you need to suppose a relation or a constant radius for all the objects. And how you determine your radius in your objects?
Well, in our case, basically they are most of them are resolved. So in that case, we assume it's the PSF size, because we cannot resolve in the inner parts. For those that are resolved, we measured it directly, but we have not projected them, which is also a problem, because we are lacking outflow models that tells us how the outflow is propagating in the galaxies. And so if we cannot project them, then of course every radius that you are going to measure is wrong, because there is some extra component that you are not taking into account. But yeah, in any case, for our liners that are compact, we are assuming that is the size of the PSF. We cannot do anything.
That is related with the question of
Yeah.
paper, okay?
Yeah, I know. So that's why I said that we need to take a step back, because I mean, if we cannot determine the radius well, then how are you going to determine it's going to be wrong already, and you start to sum up all the uncertainties, and then you end up with something that's probably not something to be compared with.
More questions?
Thanks for the talk. The elephant in the room, the radio jet. I mean, is for 7172, is there a radio jet? No. And in your sample of James Webb, are you is covering also the radio emission, so you can compare radio jet outflow with in host galaxy with radio jet?
No, I don't think that was the initial objective of just focusing on the radio. So the thing is that what they wanted to do is to select galaxies that had more or less the same AGN host, so that the differences in the outflows should come from other things. But the radio was not one of the things that was taken into account. But I cannot tell you how many of the radio because I don't know.
Last one. Promise. For the optical analysis of low luminosity AGNs, it was a big issue to subtract its contribution. What do you think for the case of the James Webb telescope?
For some objects, it's an issue. For some others, it's not relevant in the sense that what we are doing now is to analyze the emission lines, and they are so strong. And I mean, it's a huge difference between analysis of the liners and the JWST. So many of the cases, it's actually not necessary for doing what you want to do. That is basically analyzing the kinematics. But there are other galaxies that have really strong continuum, and in those you have to take it more carefully, the analysis definitely, because if not, you're probably going to have problems. But in this case, it's enough for what we have.
Okay, I think we can close the talk here. With thanks again, Laura.